Hello and welcome to today's video. In today's video, we're going to be going over topic 5.1, finding areas. So, in general, there's two very big ideas in calculus. One of which is approximation, or which we really use in derivatives. Derivatives are these wonderful tools that we use for approximating functions around a certain point. And then we come to the second very big idea of calculus, which is areas. It's very interesting for these two almost seemingly very different things to be in the same classification of math, isn't it? Well, as we go into the next few videos, we're going to see that these two topics are linked incredibly closely together, and we're going to start building the framework for that today. So I want to start by asking, how do we find the area under a curve? Well, let's go a bit simpler. How do we find the area of a rectangle? Well, it's just the length times by the width of said rectangle. What about how do we find the area of a triangle? Well, as we've been taught since geometry, and maybe even sooner than that, it's 1/2 the base times by the height. But this is where it starts getting even more interesting. What if we have a shape like a hexagon? How do we find the area then? Well, in the case of the hexagon, we divide it into smaller regions. In fact, we divide it into triangles. And what we're going to find out is sometimes, or in fact this can be said for all of the time, we can use rectangles or other shapes to divide up the area of other shapes, in this case curves, to find the area under the curve. So, taking an example of looking at f of x right here, you may notice that I have several rectangles drawn out. So what we're going to be doing in this chapter, we're going to be taking the sum of these rectangles, which are going to have a width of change of x and then a height of f of x. And that's this really big idea that I want to get across. So before we do anything else, we need to understand what it really means, or what summation notation is. So if I'm saying that I have a sum, okay, so let's say here, I'm given this symbol, which this symbol right here is called a sigma. This sigma represents to add something together. In fact, it means to add starting with this bottom number. You'll notice that it says I is equal to m. So whatever I is equal to, that's going to be where you start. And then this n means that we're going to stop when I is equal to m. N, sorry. So if I'm saying that I'm adding the sum of a of I, we're going to be adding a of m plus a of m plus 1 plus a of m plus 2, all the way until we reach a of n minus 1 and then a of n. Alright, well, we now need to know just a few very useful sums to know, or rules rather. So if we have a constant times by a, well, it's going to be the same thing the sum of a constant times by a. We're going to get the constant is times by the sum of a. If we have two things being added or subtracted, let's say we're taking the sum of a plus or minus b, then it's going to be equal to the sum of a plus or minus the sum of b. Alright. Well, now if c is a constant and n is a positive integer, then I is going to be equal to n well, then we can say the following. The sum from I is equal to 1 to n of 1 is equal to n, because we're adding 1 n times. Alright. We can also say c times by n is equal to the sum, or sorry, is equal to c times by n. We can say that the sum from I is equal to 1 to n of I is equal to n times by n plus 1 over 2. We can say the sum from I is equal to 1 to n of 2n of I squared is equal to n times by n plus 1 times by 2n plus 1. And finally, we have n, the sum from I is equal to 1 to n of I cubed is equal to n times by n plus 1 over 2, all of which squared. So now what we want to do is we want to start using these rectangles, really, to find the area under the curve. And we're going to then also use the summation notation to help us with that, especially whenever we're moving on to the limit process. So I want to start out by asking, if we're using 4 rectangles, we want to estimate the area under the curve y is equal to x squared on the interval from 0 to 1, what do we do? Well, we are going to divide this into 4 subsections with a change of x. Change of x in this case is going to be 1/4. So we can clearly see that from this we're going to get some rectangles that look like so on this graph. And really what we want to do here is we want to sum up all of these rectangles. And I want to fix that. Alright, there we go. And once we do that, we see that we're going to get 9/16 times by the base, which the change in x is 1/4, plus 1/4 times by 1/4, easy math right there, plus 1/2 times by 1/4, and that is going, and then plus 0 times by 1/4. So summing all of this together, we get 9/64 plus 4/64 plus 8/64. So we get 9 plus 4, that's 13, plus 8, that's going to be 21/64. However, you may have noticed that even with these rectangles, we have this unaccounted area. So what we're going to do now is, instead of using what's called a left-hand sum, which is taking the area of the triangles with the left endpoint, we're going to be taking the right-hand sum. So we're going to be using this right endpoint. And then here in a moment, I'm going to show you how to write those in the same notation. Okay. So now we have these rectangles, as I'm drawing in green. Okay. And I'll use green for this. So we can see that this is going to have a height, or this first rectangle that I'm adding. Let's call this, or rather, let's call this rectangle 1, 2, 3, and then 4. So we have to multiply the height of this first rectangle, which is going to be the value at 1/4. So we get 1/16 times by 1/4 plus 1/4, which is the height at 1/2, times by 1/4 plus 9/16, because that's the height of this third rectangle, times by its width, which is 1/4. And then finally, we're going to add the height of this next rectangle, which is going to be 1 times by 1/4. So now we get 1/64 plus 4/64 plus 9/64 plus 60. All right, that would be 4/64. All right. Now we just have to add up the totals here. And we can see that 1 plus 4 is 5, plus 9 is... Sorry, this should be 16/64. I apologize. 16/64. Okay, so we get 1 plus 4 plus 9 plus 16. That looks like the sum of squares, which it should really look like that. So what we're going to get is 5, 14, 30/64. And now what we're going to look at is what area was unaccounted for whenever we did this right-hand sum. And we can clearly see that we have quite a lot of area that's unaccounted for. So, earlier I was talking about notation for this. And what we're going to say for notation is a right-hand sum with n rectangles is going to be equal to the sum of I is equal to 1 to n. This is the same n. It just represents the amount of rectangles of f of x of I times by the change in x. What is change in x, you may ask? Well, I haven't really talked about it yet, but the change in x is equal to the end point of the interval minus the beginning point of the interval all over a. Or sorry, not all over a, all over n, the amount of rectangles. Well, a right-hand sum really means that you're going to be using the right endpoints instead of the left endpoints, or you're going to start from the right instead of the left. If you're going to take a left-hand sum, so it's denoted as L of n, is equal to the sum of I is equal to 1 to n of f of x of I minus 1 times by a change in x. And the change of x is still the same. Now you may ask yourself, why does this work? Well, I'm going to draw out a graph real quickly, and let's say we have... Alright, actually, I don't want that like that. I want it to be like so. Okay, so we have our graph here, and we want to find or estimate the area from A to B. Well, we're going to use little triangles to do this. Or not triangles, rectangles, I apologize. Each of these rectangles is going to be a change in x, a b minus a divided by the amount of rectangles. However, its height is correspondent, if we're using a left-hand sum, to this left endpoint. Which just means that it's starting at A. If we are going to be using a right-hand sum, it has the same change in x, this b minus a, but now its height is going to start at b. However, it's still going to only have the same amount of rectangles, so we're going to have to exclude a point. So really just like drawing this out really for us. There we go, there we go, there we go, there we go. Cool. That's about right, it looks like, at least. So we're going to just be using the left endpoints, or at least we're going to be starting at x naught rather than x of 1. So this is really just saying, like, this first x value. This is x of 1. This is x of 2. This is x of 3. This is x of 4. This is x of 5. And so on and so forth. So really, instead of saying starting at x of 0, the right Riemann sum starts at x of 1. And the left Riemann sum starts at x of 2. Going forward, I want us to work on finding the exact area. Well, from A to B. So what really is this really cool idea, and what connects the derivative to the area, is the fact we're going to find both by limits. Recall that the definition of the derivative is the limit as x approaches a of f of x minus f of a all over x minus a. Well, if we want an exact area under the curve, what if we take the limit what if we make it so we have an infinite amount of rectangles? So what if we say the limit as n, the number of rectangles, approaches infinity of the sum from I is equal to 1 to n of f of x of I times by a change in x. And what we will find is this expression right here will give us the exact area under the curve. So let's work an example on let's find the area of y is equal to x squared plus 1 on the interval from 0 to 3. Well, what is this going to really look like? Well, we're taking the limit as n approaches infinity of a sum from I is equal to 1 to n of f of x of I times by a change in x. What is our change in x? We know change in x is equal to 3 minus 0 all over the amount of rectangles, which is n. So we're going to say that this is going to just be 3 divided by n. Now what we're going to do is we're going to expand this out a little. So we're going to actually say this is going to be the limit as n approaches infinity of f of x. Well, f of x of 1 is going to be 0 plus the first change in x. Because we're starting at this second rectangle. We are starting here at x of 1. So, we're going to then add f of 0 plus 2 times by 3 over n. Plus f of 0 plus 3 times by 3 over n. And we're just going to keep adding this until we reach f of 0 plus 3 times by, n times by 3 over n. And now what I want to ask you is, what is the value of n times by 3 over n? That is just 3. So we can clearly see that our x values have made it to the end of the interval. But we're not done yet. Now we actually have to plug in these values into our function f of x. So we get the limit as n approaches infinity of 3 over n squared plus, our function is 1, plus 2 times by 3 over n squared plus 1. And we're going to keep doing this until we reach n times by 3 over n squared plus 1. Well, we can simplify this. We're adding 1 n times. So this is really just the same thing as the limit as n approaches infinity of n. But then we're adding. Let's expand out these squares. We get 9 over n squared plus 4 times by 9 over n squared plus, let's see, then we would be 9 plus 9 over n squared. Not plus, sorry, times by. And then we'll eventually get to this n squared times by 9 over n squared. And what this is really telling us is this is the sum of squares. So what we're going to do is we're going to factor out a 9 over n squared from everything. And we're going to write this as a sum from I is equal to 1 to n. Well, we are summing squares here. We have I1 here. We have 2 here. This is 2 squared. We have 3 squared. And it goes to n squared. Alright, now what do, you might ask? Well, we now have to sub n. Ooh, you know what I did? I left out a very crucial 3 over n. There we go. Let's add that in. And now all of the math should work out, hopefully. Okay, so now we have to sub in what this summation is equal to. We know that the sum of I is equal to 1 to n of I squared is equal to n times by n plus 1 times by 2n plus 1, all over 6. So, we can substitute this into our limit. So we get the limit as n approaches infinity of 3n times by, 3n times by n plus 9 over n squared times by n plus 1 times by 2n plus 1 all over 6. Now we're going to distribute this 3 over n into the limit. So we get the limit as n approaches infinity of 3 over n times by n. That's just 3. Plus, and we're going to kind of simplify this here. We're going to get a 3 over 2 plus 9 times by n plus 1 times by 2n plus 1 divided by 2. Well, allow me to ask you this question. What is the limit as this approaches infinity? Well, we have to do a small bit of fuzzy math. Or sorry, n cubed. There should be an n cubed here. And there should be an n up here. There we go. So now, as we take the limit as n goes to infinity, this 3 is just 3. It doesn't have any n's in it, so it doesn't change. But we have to look at the terms that do. And inside of this function, the terms that are going to denominate are going to be the highest degree polynomial. Or really the coefficient of the highest degree polynomial. Or the highest power of x. We want to really be looking for what is going to have the highest power of n. And the answer is, whenever we expand this out, there's going to be this 2n times by this n times by this n times by this 9. And that is going to give us an 18n cubed. And this is what's going to dominate as it goes to infinity. Well, in the denominator, what's going to dominate as n goes to infinity is n, or 2 times by n cubed. So now what happens is these n's are going to just slowly become more and more like each other, and this is going to equal to 9, or 18 divided by 2. So finally we get an answer of 12. And then here in a few videos we'll learn how to verify this answer. But what we have done here is we've found the exact area under the curve. This isn't just the estimated area. No, this is the exact area under the curve. And that's the really cool thing about calculus. So, let me ask you, so earlier in this chapter, or not in this chapter, but earlier in my series of calculus, we discussed what was known as the velocity problem. How do we know the velocity of a car moving or at any given point? Well, the velocity is always changing, and that is true. But now, our issue that we have is, what if we are given a velocity but want to get back into position? And the big issue with this is, as of right now, we can't really do that. You can't take a derivative of velocity and get position. You can take the derivative of position and get velocity, but we can't go the other way around. Well, let me ask you this. Let's just take one small moment here. Let's plot these data points on the curve. So we have 0, or actually, I'll do that, and then I'll be back in a moment. Well, now that I've sketched this on the curve, let me ask you a question. What is velocity times by time? Well, if we're given a continuous velocity, velocity is really just miles per hour, or it's a distance unit divided by time. So, and now I want to ask, what if we multiply it by time? Well, we would normally get a distance. So, what really calculus here can give us is a tool to estimate the distance traveled, or rather the displacement. So, looking at this graph, we have a velocity value times by a time value. So the area underneath this curve is really going to be the displacement. So this area problem is connected to the distance problem, just like the velocity problem, this velocity problem, just like the other velocity problem, is connected to the derivative. So now I just want us to estimate the distance traveled using the intervals provided. Let's use a left-hand Riemann sum. So I always like to start out by writing my sums. I'm going to delete that. So I get the sum, if I can write, the sum from I is equal to 1 to n of f of x of I minus 1 times by a change in x. Well, what's our change of x for all of these? It's 10. So we're just going to take that out of the summation. So now, expanding the summation, we get 50 plus 70 plus 31 plus 43 plus 59 plus 71 plus 65. Okay, 50 plus 70, that is 120. Plus 31, that is 151. Plus 45, that would be 196. Plus 59 would be 255. Plus 321, no, 326 plus 396, I believe, times by 10. Oh, I meant to say 391. Sorry, there we go. And then multiplying that total by 10, we get a grand total, an estimate of 3,000. Sorry, I actually lied to you. So we are only going to a grand total of 7 rectangles, and this is 8 terms. Nope. Sorry, 6 rectangles, and this is 7 terms. And because we're using the left-hand term or side, we do not use 65. So what we really get is 10 times by 391, or sorry, 3 times by 391 minus 71, which we'll see is 320. So our final answer here is going to be 3,200 for the total distance traveled in miles. Yeah, like 32,000 or 3,200 miles. I apologize. Well, that's all I have for you today. I'm looking forward to going over integral calculus with you all, and I hope you all have a wonderful rest of your day and found this video informative.